So a lot of people have been asking for a tutorial on shaders with Pygame, and I figured that since I'm more comfortable with the topic now, I would finally go ahead and make that tutorial, because there's really not much out there for doing shaders with Pygame. So Python itself is too slow for individual pixel calculations, and that's kind of the root of the problem and the reason why you'd want to use shaders. Shaders allow you to do modifications on an individual pixel level efficiently. This gives you the ability to do all types of graphical effects that you couldn't otherwise do. So the problem here is that shaders are dependent on the GPU. To use shaders on the GPU, we must use OpenGL. OpenGL is kind of an interface for our GPU. Pygame is meant to run on the CPU by default and isn't set up for GPU-based rendering. There's a whole separate pipeline for GPU-based rendering where you're using OpenGL. Fortunately for us, Pygame has a flag during window creation for creating an OpenGL context so that we can use the GPU with Pygame. This prevents us from drawing to the screen the way we normally would with Pygame. Instead, we have to use the OpenGL pipeline to render. So you might be wondering at this point, why are we using Pygame if we're using OpenGL to render through Pygame somehow? Well, Pygame is actually more than just graphics. It handles the input for us. It handles things like audio, and we can still render to surfaces. The important things, we just can't put that directly onto the screen. So in order to keep the convenience of using Pygame and Pygame surfaces the way we would normally draw in Pygame, while getting the graphical functionality for shaders from OpenGL, we can render Pygame surfaces as we normally would, but then instead of rendering it to the screen at the end, we would then convert the surface to an OpenGL texture and then render that in an OpenGL pipeline using shaders. This way we can do post-processing with shaders in OpenGL. If that sounds a bit complicated, don't worry, I'll go through in this tutorial how all of that works. Normally you would use OpenGL through wrappers like the PyOpenGL module, but that's very tedious and there are newer solutions that are more convenient. In this tutorial, I'll be using ModernGL. It's less documented, but it's a lot more, as the name implies, modern. It fits a lot better with object-oriented programming, and it handles a lot of the kind of boilerplate stuff with OpenGL. If you actually look at the code, it's like sometimes OpenGL will be 4 or 5 times more code than using ModernGL. It's important to note that I'll be mentioning OpenGL and ModernGL separately a lot in this tutorial. OpenGL can be thought of as the stuff going on under the hood. Most games that use the GPU are using the OpenGL pipeline, so anything I say about OpenGL transfers to other languages and use cases. When I talk about ModernGL, I'm referring to the Python wrapper, which is specific to our use case. I'll explain the OpenGL pipeline in a bit, but first let's make a basic application to run shaders on. So we can just start with our basic import Pygame. Next, we can just create a window as we normally would. We'll kind of change this up in a bit. But for now, we can just create our window by doing screen equals pygame.display.setMode. And then let's do our pygame.init up here as well. And we need a clock, so let's do clock equals pygame.time.clock. You should hopefully be familiar with Pygame if you're watching this tutorial, so this shouldn't be confusing at this point. Let's pull in an image just to work with. So we'll say image equals pygame.image.load, and we'll do image.png. This is just a screenshot from my game, Hue Flowing. Any image should be fine here. I'm just using it for demonstration purposes. And then we can get straight into our loop here. Let's just fill our screen with black. And then grab our input. And we can do if event.type is that pygame.quit. And we also need sys, so we can do import sys up here. And then sys.exit. So we can close our window. And then let's do a screen.blit image at pygame.mouse.getPosition. So we'll just render our image where our mouse is, and then we can do pygame.display.flip, and then clock.tick60. All right, so we should be able to run this, and as you can see, we've got our image here. If I move my mouse, you can't see my mouse, but if I move my mouse, I can move around the image. And if I click X, the window closes. So that's just a standard Pygame application. So I'm going to show you how you can take this application and then you can convert it to something where you can use shaders on top of it. So if you notice, we're using Pygame functionality for rendering here. We're rendering onto the screen, and then we're using a Pygame surface that is our image and rendering it at our mouse position. So we're doing all this Pygame stuff, even with our rendering, and then we'll just send that over to OpenGL and render that. So, unfortunately, I'm going to have to hit you with the rundown of the OpenGL pipeline, because OpenGL is not as simple as, hey, take a texture, put it on the screen, run shaders. It's not that simple. So I'm going to have to hit you with the rundown for how all this works, and then we can get started on writing the ModernGL code. Because otherwise you're going to get very lost, because OpenGL's not quite the way you'd expect it to work. Because I think most people, and I thought it this way too, would expect it to be put a texture on the screen, use a shader. So in reality it's much more complicated. I'll try my best to just cover what you need to know for this specific use case, because there's a lot more to learn about. And funny enough, even most of the OpenGL tutorials don't even scratch the surface of all the stuff that you can do with the OpenGL pipeline. So the best place to start with this is what a shader exactly is, because there's some misconceptions here, and you need to kind of understand what it is and how we use it and just how that works. So a shader is basically just a program that we can write that will run on the GPU. If you're unaware, the GPU is special because it can run a ton of small tasks in parallel efficiently. Anytime we write a shader, it's being run in parallel for each of something. There are a lot of different types of shaders, but there are only two that are important for what we're doing. We'll be using vertex shaders and fragment shaders in this tutorial. Fragment shaders are responsible for doing what most people think of when they think of shaders, since they run in parallel for every fragment, which in our case is pixels on the screen, to determine the colors shown. Since you're computing all these colors, you can do things like add shadows and stuff like that. The other shader we're using, vertex shaders, are a bit more complicated, and this is kind of where we get into the weeds of why the OpenGL pipeline is a bit bigger than you might have initially thought. So vertex shaders are run per vertex to calculate transformations for each vertex. So when I say vertex here, I'm talking about the vertex you learned in geometry, which is the connection of the edges in a shape. This might sound a bit strange for a 2D application, since we're drawing with pixels and not textured polygons in 3D space. But when it comes to OpenGL, we have to have a geometric object to color. There is no such thing as just drawing to the screen in OpenGL. It's easy to think of it as having to create a rectangle in 3D space to draw onto. That's really what we're doing. Normally, vertex shaders would be responsible for handling movement in polygons. If a camera moves in a 3D game, the whole world has to move. When 3D geometry moves in a 3D application, it's the vertex shader that's responsible for those transforms. It's also responsible for the placement of different objects in the world. You can have one definition for a shape of a rock, but place it anywhere in the world. This is the job of the vertex shader. The math gets pretty complicated and it involves a lot of matrices, but fortunately for us, the rectangle we draw for our game doesn't need to move. So we can define our rectangle in world space and tell the vertex shader to leave it as is. You might be wondering if it's possible to just take out the vertex shader, since it's not doing anything to the data we're giving it for the vertices, but we can't. In OpenGL, we're supposed to use the vertex shaders to define geometry for everything. It's just part of the pipeline. With what I've mentioned about shaders, I can now explain the overall process for the rendering pipeline, and it should make sense. We start by creating a buffer of data that defines our geometry. In 3D applications, this could be generated from a 3D model, but in our case, we can just write it by hand since it's a rectangle. This buffer can contain information aside from the vertex coordinates as well. In our case, we'll be giving coordinates that describe how a texture should be applied to the geometry. These are referred to as UV coordinates. We'll have to pass this data along through our vertex shader to our fragment shader so we can apply our texture that we made from a Pygame surface to our rectangle there. With our vertex and fragment shaders written, we can define our shader program, which is the combination of our vertex shader and our fragment shader. Then using this program and our buffer, we can define our render object. ModernGL actually calls these vertex arrays, but the name is a bit misleading since it has a shader program associated with it. Under the hood, it's made up of multiple OpenGL objects, so I'm just calling it a render object to make things easier to understand. It contains geometry and programs for drawing that geometry, which is almost everything you need to render something. The final step is to use this render object every frame to render the scene. Any changes to the scene are given to the program as uniforms, which are basically just inputs to shaders. We can take in uniforms from either the vertex shader or the fragment shader, but we'll just be using them for the fragment shader in our case. For this tutorial, I'll show you how you can take in a texture and the time or any float as input. You can check out my game Hue Flowing's code if you want to see a more fleshed out example of the types of things you can do with shaders. Anyways, with that mess of a graphics programming introduction out of the way, we can finally get started. So we must start by defining our input data for our whole scene. So let's call this our quad of buffer, and then we'll set it equal to ctx.buffer, and then we'll do data equals array f, and then we just make a list here and open that up. I don't want that. Open that up. So a couple things we have to define first. So CTX, that'll be our context for rendering in the OpenGL pipeline, or just the context for the OpenGL pipeline itself. So we'll do CTX equals ModernGL.create context, and to do that, we have to do import ModernGL. If you don't have ModernGL, you just install it with pip. ModernGL is just pip install ModernGL, so just make sure you have that. Anyways, so the other thing we need here is we need array. This is just a library within Python for handling arrays. It's more efficient than just using lists. But for that, we do have to define a data type. That's what this f is here. So this f is just saying that our data type for our array is a float. And then this list right here is just the data for our array. So we can fill out our array right here. This is going to be a bit confusing. We have to put in a bunch of individual values in a single array, and then later on we'll have to define how OpenGL interprets this buffer. So for right now, we just kind of throw in the data. We have to keep track of how we're formatting things, but we're not really telling OpenGL what this data represents yet. It's just a buffer of data. As I mentioned before, we'll be taking the coordinates for the vertices, and then we'll also be taking the UV coordinates, which are used for applying textures. So the way we'll format this is we'll do the X and Y of the vertex coordinates, and then the X and Y of the UV coordinates. Normally in 3D programming, you do X, Y, Z for the vertex coordinates. But in our shader, we can just kind of account for that and just take in the 2 and then fill in a 0 for the z-axis to say that we're not really using the z dimension. Anyways, so we do -1, 1, well, these are floats, so let's do .0, 0.0, and 0 again, and I'll put the format here just so you can see. We get position XY, and then we get UV chords XY. And then I'm going to put a new line here because each line can be thought of as a point. And then even though this is just a single array, it's one-dimensional, we're just breaking it into sections of 4. So we'll go to a new line. This is a different point, but we need to define new data for it. So for this one, we'll do 1, 1, and then 1, 0, and then we'll do -1, -1, 0, 1, 1, -1, 1, 1. So this is probably confusing. So a couple things to note. First of all, the coordinates in OpenGL for vertices are actually, for everything, it uses kind of the mathematical Cartesian coordinates where positive on the y-axis is up. However, Pygame uses the inversion of that where positive on the y-axis is down. So we have to do a bit of a conversion here, and that's where these numbers get a bit funky. You can skip ahead a bit if you're not interested in hearing this explanation, but I'll go through it anyways. The coordinates in OpenGL are -1 to 1 for both, or actually for all axes. We're just using 2 of them, but it goes from -1 to 1, and then for UV coordinates, it's actually 0 to 1. That's why you don't see any negative numbers on the right half of these sets of numbers here. So we start with this, which is the top left, -1 and 1, because if you think about it, it's -1 on X is left, 1 on Y is up, so you get top left. And then 1, 1, which is going to be top right. This is going to be bottom left, and then bottom right. So I'll label these right here. So we get top left, top right, bottom left, bottom right. So if you look at the UV coordinates, they do kind of line up. It's the same thing, except it also has to account for the fact that we have to flip everything on the y-axis in order to account for how everything in Pygame with respect to OpenGL is upside down. There are multiple places you could do this flip at. I'm doing it here in this data. You could also do it in the shaders as well. There's a couple ways you can do it, but I like it here because then you can just kind of write your shaders as if everything's right side up. So in 3D rendering, normally everything is a triangle. We'll be using a rendering technique called a triangle strip, where it kind of takes a bunch of connected triangles, or it generates a bunch of connected triangles from a couple of points. So the way this ends up working for us is we get the triangle of the top left, the top right, the bottom left. That's one triangle. And then you see this one extra point here, and you're like, what? There's not another 3 points here. But actually, how this works is it takes then the bottom left, the bottom right, and then the top left to create that second triangle. And then those two triangles together end up making a rectangle. So if you actually kind of try to draw out, like connect the dots on this, you would end up with kind of the shape would cross itself. It would form a Z shape, which isn't quite what you'd expect for a rectangle, but the reasoning there is because of the weird way the triangles get joined together. You can play around with this if you want to see how that works, but it can get a bit confusing. Anyways, so that's one of the hairier explanations out of the way. Let's get into the vertex shaders and the fragment shader. So the vertex shader is pretty easy. This is using a different language, GLSL, to write the shaders, but we can just write them in Python as a string, and then they get loaded in. You can also write GLSL into its own file, load that in, convert that to a string, and then actually create a shader out of it. But for the purposes of this tutorial, it's easy to just write it as a string. So we'll do vert shader equals, and then we'll do a multi-line string here so we can just write text. So the first thing you have to do in a GLSL shader is define the version you're using, because there's a million different versions and the syntax is different between different versions. It's not really assumed what version you're using, so you need to specify here. So we're using 330 core, which is OpenGL 3.3. There's different features, the syntax is different, it gets kind of messy, but it's not too different. It's too difficult to adapt to different versions of OpenGL with GLSL. Anyways, so the way a vertex shader works is you take in the input of the vertices and you spit some vertices back out. So fortunately for us, the syntax isn't too complicated. You do in and then vec2, this is the data type right here, and then we'll say vert, and then we can do in vec2 text chord. So what we're doing here is we're describing our inputs. That's what the in keyword's for. We'd say our data type, which is a vec2. That's a vector2. Think of it like a tuple with two values, so like 1.0, 2.0, something like that. By default, if you don't say otherwise, this is a float. So there's, I believe it's vec_i2 or something like that. If you want to have vectors of integers, there are use cases for that, but for most things you just use floats. It actually might have been vec2i, I forgot. All right, so this vert here refers to the vertex coordinates. That's going to be the first two numbers for each one of these points here. This text coord is going to refer to the second two values here that are the UVs. And then, so the last thing we need to do is just kind of say what we're sending out of our vertex shader. So we're going to say vec2, and we're going to have our UVs going out. That's just, we're basically just taking these values, the UVs, taking them in as text coord, passing them out as UVs, just kind of as is. And then you might be thinking, well, we also need to output our vertices as well, but it's built into the way vertex shader works, so we don't specify it here. So in shaders, you'd have to define a main function, so we'll do void main. If you don't know what void is, that just means that it doesn't return anything, which is a bit deceiving because we do assign to something. The thing we assign to is GL position. This is going to be, this keyword refers to the vertex we're outputting. So we can say vec4, and then we do vert 0.0 1.0. So the syntax here gets a bit confusing. So first of all, GL position, that's the vertex coordinates we're outputting. It's equal to a vec4, which is kind of a tuple of 4 values. So you might be wondering, so well, first of all, it's like 1.0, 0.0, -1.0, 5.0 or something like that. You might be wondering, why are we sending out 4 values? Are these other 2 values here the UVs? No, they're actually not. That's all just for the vertex coordinates. Also, there's the issue of you see 3 values here, and this is a vec4. So to make this simpler, I'm going to say vert.x and vert.y for now. I'll simplify that later. So we're dealing with 4 values here. We've got the x coordinate of our vertex, the y coordinate, and then this is where we're adding in that part that I mentioned before, where it's actually 3D and we're converting our 2D to 3D. This is where we're saying that our z coordinate is 0. So everything is just at 0z, there's no depth. And then over here, we have a 1.0. So this is a bit confusing. The reasoning for this is, in short, math. There's mathematical reasons for using an extra value here. It kind of represents a scale, sort of. I would recommend don't touch this number. For the most part, you don't touch this number. It's useful when you're doing matrix multiplication and stuff, but it's so widely used in the math for 3D just calculations that it's just kind of required. If you leave it as 1.0, it doesn't mean anything pretty much. It's the same as just the 3 coordinates, the way you would expect it to work. So just leave that as 1.0 and don't touch that. If you want to look into it, it's called the homogeneous coordinate. It's not super important for what we're doing. Anyways, as I promised, we've also got to pass through our UVs. So we'll take our UVs and we'll just assign it to text coord. That's all we have to do. We just have to say that thing that we took in is also the thing we're sending out. All vertex shaders are required to just set a position here, so but we're not required to output UVs. That's why we have to specify it here. Anyways, that is our entire vertex shader. You usually don't have to touch this for the types of things we're doing. There are some rare cases where you might want to touch this, because this is really just a place where you can modify the shape of the rectangle we're using to represent our screen. There's one last thing, actually. We can actually take this and shorten it down to just a vert. In GLSL, if you have, say, a vec2 and you feed it as an argument to another vector, it gets kind of splatted out, is the Python terminology. So if I just pass in vert like that, it's equivalent to doing vert x and vert y, because vert has 2 values because it's a vec2, and then it becomes a vec4 because, yeah, the 4 values. Anyways, so that is our vertex shader. Now we can do the fragment shader, which is where all the fun's at. So this works pretty similarly. So we do version 330 core, and then we can do out vec for f color. So we're specifying here what the color we're outputting is, and then we need to also specify our input. That will be our UVs, and then we'll have a main function. So to start with, I'm just going to say f color equals vec4. We'll do texture text, and then I'll say UV dot RGB, and then we'll put 1.0 there. Now we need to define our texture that we're using here. So this is where we use uniforms, which I mentioned before. So we do uniform sampler 2D text. So a uniform is a different type of input. So there's 2 types of inputs here. We have the in type of input, which is a different value for every instance of the shader because it's run in parallel. And then we have a uniform. And the reason why it's called uniform is because it's the same for every single process running in parallel. The in type of input is defined in the buffer we got up here. We'll actually define how it interprets that in a bit, but it comes from this buffer. The uniforms are easier to modify during runtime, and I'll show you how to do that later. This is the reason we pass textures in here, is because our texture that we're using is changing every time, and well, actually regardless, you would pass the texture in as a uniform. So sampler 2D just kind of refers to a texture, sort of. It lets you sample values from a texture. That's why it's called sampler. You can tell it an X and a Y, and you'll be able to pull out a color. So that's what this texture function does. You pass it the texture, and then you pass it coordinates, which were the ones we passed through here, which came all the way from here. But yeah, you give it the coordinates, it'll give you a color. And then we take the RGB value of that color. Funny enough, this texture thing, I can't remember if it's a vec3 or vec4. I think it's vec4, but it's a vec, so you can do technically x, y, z, and s equivalent. So x, y, and z refer to the first 3 values, but so do RGB. It's just a thing to make things more readable. You can also do .r just to get 1 value, .rg to get red, green, which is 2 values, or RGB in our case. And then the reason this is a vec4 is because of alphas for transparency. So we say 1.0 because we don't want any transparency. I think you have to do, there's some stuff you have to enable somewhere else if you want to do proper transparency though. Anyways, in summary, we take in our texture, we take in the UVs, we sample our texture with the coordinates, and then we use the color from the texture and assign it to our output color. Remember, the fragment shader in our case is being run for every single pixel. Or more specifically, we're going to be running it for every single pixel that's a part of the shape we defined up here and in our vertex shader. So kind of the vertex shader will generate some geometry that gets filled in by the fragment shader. So the fragment shader runs for every single pixel in that geometry, but since our rectangle is our whole screen, you can think of it as running for every single pixel on our screen. All right, so now our next step, now that we have our shaders defined, is to create our shader program, which is just kind of a bundle of the vertex and fragment shaders. That's pretty much all you need to think of it as. So we just do program equals ctx.program. And then we pass it vertex shader equals vert shader, fragment shader equals frag shader, and that's that. So that'll bundle them up. Technically, this will also compile the code because unlike Python, GLSL is compiled. It gets compiled and then run on the GPU. So this will compile it. This functionality here from ModernGL removes a lot of the extra boilerplate you would have to write in normal PyOpenGL code, for example. So the next step is to define what I'm calling the render object. So we'll do render object equals ctx.vertex array. Like I said, the name is a bit misleading because we give it our program. So it's our shader program that can do the transforms and the coloring and everything. And then this is where we finally tie it in with that buffer that we defined up here. So let's give it our quad buffer, and then we'll do 2f vert text chord. All right, so this is where things get a bit interesting. We have 2f. This is the format specification for like just kind of how the buffer gets interpreted. So we get 2 floats and 2 floats. And then for every thing that we define in this string here, we have to give it a label. So we're calling this first 2f vert. So this is 2 floats. That's vert. And then our second 2 floats are text chord. So this is how it breaks down this quad up here. So it'll say the first 2 values are going to be the vert, and then these 2 are going to be text chord, and then it'll cycle. And once it gets to these ones, it'll do vert and then text chord again. It just keeps going. And then these names right here need to match the in values in your vertex shader, which they do for us. So this right here just kind of ties everything together. It gives it the program, it takes our buffer, it tells it how to interpret the buffer and apply it to our vertex shader, and then the vertex shader also kind of has the out, which is the in for our fragment shader and everything. So this is everything we need to render, like sort of. There's some extra steps we have to go through, but this is kind of the core rendering object, as I call it. So the next thing we need to be able to do is define a way to convert a Pygame surface into an OpenGL texture. So we can do def surf to texture surf, and then we do text equals ctx.texture surf.get size 4. Okay, so what we're doing here is we're creating a new texture under our OpenGL context, and then we're telling it the dimensions. So this is just a tuple of the size from our surface, and then the number of color channels. So in our case, we're saying 4 because we want red, green, blue, alpha. And then we can do text.filter equals modernGL.nearest. So these define how the transition between pixels should be handled in the rendering of textures. So let's say, for example, you had a like 2 pixel by 2 pixel texture, and then you were rendering it onto a rectangle that was actually the size of your whole window, which is hundreds of pixels. So you have to kind of extrapolate those 2 pixels of your texture onto those many extra pixels of whatever you're rendering onto. So this just kind of describes how you do that interpolation to generate in-between colors. So there are different filters for the interpolation. Nearest is the one you want to use if you're doing pixel art, because that makes everything pixel perfect. Like there's no blurring of the colors. If you don't do nearest, there's other options. I think one of them's bilinear, where it'll merge the 2 colors together in the space between the where the original pixels were on the texture. So if you want kind of a smooth, not pixelated scaling when you make your textures bigger, you would use other filters. But for pixel art, since that's what I do, I use nearest. You can look up the other ones if you want to. Text.swizzle equals BGRA. This is defining how the channels are kind of mapped to each other, because Pygame uses a different order for colors than OpenGL does. So we just have to swap around the channels, and this is just kind of telling you how to do that. If you don't do this, you'll see the colors get mixed up when you render. So the next thing is to actually fill this texture with data, because we just kind of defined a bunch of information about the texture. So we said the size, we said how we want it to scale, we said how we want the channels of the data to be interpreted. So the last thing we have to do is to say what is the data that's this texture is using. So we do text.write, and then we do surf.getView and 1. So Pygame has some functionality for generating the data we need to create this texture. So you can look up the getView function in the Pygame documentation if you want. It just kind of generates, I don't know if it's a binary output, it's some kind of lower level output for the surface. And then the 1 is just specifying what the format should be. So this is just kind of getting the raw data for the surface, then we can just throw that into the texture. This is kind of just saying how it's interpreted. Anyways, so from here we can return our texture. So this function will now take a Pygame surface and return an OpenGL texture, which is great. So the next step here is to actually switch our Pygame window over to an OpenGL capable Pygame window. So as I mentioned, we use some flags for this. We can do pygame.opengl and then a pipe pygame.doubleBuff. If you don't know, the pipe is just how you apply multiple flags because it's a logical OR and these are really just numbers. It's a binary math thing. Anyways, so you take the pygame.opengl and pygame.doubleBuff. DoubleBuff, I believe, is where you have 2 buffers for rendering, one that's showing like what's on screen and one that you're rendering onto for the next update. And that's why we use flip down here. So flip is what swaps those buffers. You'll switch between which one you're rendering on and which one's being shown. That's just kind of a technicality if you're curious. Anyways, so pygame.opengl is where you're actually saying, yeah, I want an OpenGL context. And then ModernGL is able to hook onto that when we do create context here. Anyways, so that's that. So we have a couple more things to do. So we can't render onto the screen anymore. So that's not going to work because, as I mentioned, you can't blend onto the screen anymore. It won't let you. So we do display equals pygame.surface, and we'll do 800, 600, same dimension as the screen. And then instead of doing screen.fill, we'll do display, because that's just a different thing now. Because the screen refers to the actual window pretty much at this point. So we need another surface we're rendering on that we're going to pass in to the pipeline. The next thing here is to actually do the legwork of the rendering. So we do frame text equals surf to texture of the display. So this is where we convert our Pygame surface into an OpenGL texture. And then we have to say we want to use this texture. This is one of the places I kind of wish ModernGL had a bit more abstraction here. Maybe they do and I missed it, but this is one of the places where you're kind of dealing with one of the lower level things that comes with the way OpenGL is set up that I don't really like. But we have to say that we're using a texture here, and then we have to say where we're using it. So we're using it at index 0, and then we can say in our program, remember our program is the combination of shaders here. It's a bit more than that because it also has its own memory for uniforms, which are the things we pass in like the texture. So we'll say text equals 0. So it would be nice if you could do just text equals frame text, but that doesn't work. You have to do this weird dance of saying you're using it at location 0, then you use location 0. You can write your own abstraction on top of this, so you can have something a bit cleaner for that if you want. I actually did that for some of my stuff. So anytime you kind of use program like a dictionary and assign a value like this, it applies a uniform value. So we're saying write to the text uniform the number 0. And the sampler 2D data type, at least when we're writing the uniforms out in the Python code, takes an integer. The next step is to actually render the whole thing. So we do render object.render, and then we do mode equals ModernGL.triangle strip. If you remember, I mentioned before triangle strips. That's that weird interpretation of these 4 points into a rectangle using 2 triangles. Well, there's a couple different ways you can render. You can actually render like connected lines. You can render quads, although best practice to use triangles. And yeah, there's a bunch of other things. You can render points. So there's a bunch of different ways you can tell OpenGL to render. Well, in our case, we're telling it through ModernGL, but yeah. So if you remember, this render object contains a reference to program. So even though we're modifying program here and we're not mentioning it anywhere else in our loop, because render object has a reference to program, this gets updated. So this line right here directly affects how this gets rendered. And then the last thing we have to do here is we have to release our texture. So we do, actually I'll do it before the clock cycle here. So we'll do frame text.release. So we have to do a bit of memory management here because, well, that's just kind of how it is with graphics programming. We allocated a texture when we did this. Every time we call this, we're going to allocate a texture. And this texture actually has its own ID and everything. So every time we call this, we're allocating a texture. If you don't free up this texture, you're going to run out of RAM in your graphics card or VRAM. And then your thing will crash. So you have to be careful and remember to free that up. Release just deletes the texture. So if I did everything perfectly, this should run now. So let's try and see. It crashed. So module is not callable. Let's see what that is. Oh, okay, I see my mistake here. So up here on the array thing, we're not supposed to just import array. If we do, we can do array.array down here. The other option is to do from array import array. That's a minor mistake. That was quite confusing. Anyways, let's see if that works now. And it does work. So if you notice, this looks the exact same as what we had before. So all we did was just kind of write the boilerplate for using the OpenGL pipeline to render exactly what we had before. But the cool thing now is that this is where we can apply shaders. We already have our basic shader code written, so we can do some funny stuff here. Just as a demonstration, let us take .rg, that's the red-green value, and then we're gonna take out the blue value here, and then we're gonna do something funny to it. We're gonna multiply it by 1.5. So that will tint the whole thing blue. By increasing all of the blue values by 1.5. So that's one of the things you can do. So you can tweak the colors in here by doing stuff like that. So now we're going to get into something a bit funner. And remember, this tutorial is not meant to be like a full GLSL tutorial. There's lots of other tutorials you can use for GLSL. There's other resources you can use after this if you want to fully learn how to do shaders, and lots of examples for how to make some cool shaders as well. But I'm just showing you the basics and just how to do it with ModernGL. Anyways, so let's set up another uniform here. Let's say uniform, we'll say float time. So we're going to take in the time. Well, we need a time to take in first. So we'll do t equals 0, and we'll say t plus equals 1. And then down here we'll say program time equals t. So this is just how we're passing in the time as our uniform. Every frame, the uniform will get updated with a new time, and then we can use this time over here to do some fun stuff. So I'm going to create another vector 2. We'll call this sample position, and it'll be defined as the vector of uv.x, uv.y. And what we're going to do here is we're going to modify the UV coordinates. So this is the mapping of the texture onto the geometry. So we're changing how that gets mapped. We'll say uv.x plus the sine of uv.y by 10 plus time by 0.01. So this is a lot of math here. So we're taking uv.y, so this is a 0 to 1 number, multiplying it by 10, and then we're adding the time that we're passing in, which is just the frame number. So we get 60 of those. It increases by 60 per second by 0.01. So this will oscillate up and down. And then, so I'm going to multiply this by 0.1 just to make it a bit smaller. So we're going to be shifting our sample x coordinate on a sine wave pattern as time passes. It'll make a lot more sense once you see what this actually looks like. So instead of now using the UVs here, we're going to use sample position. So we're just kind of warping our UVs and the mapping of the texture here. And we can do some cool tricks with that. So let's go ahead and run this. Oh, sorry, I made a mistake here. That's UVs. And then we get it. So as you can see, we get this wave-like effect on our image here. And if I move it up and down, you can see it sliding along. But it's shifting the coordinates it's sampling from on the texture based on the time and the UV coordinates that were assigned to it. So you can do a lot of really cool stuff with shaders. And shaders are all about taking just kind of the simple concept of assigning a color to a fragment And then because of the compute power you have for each individual pixel, you can do some really cool stuff if you pass it the right information. So shaders are like really an interesting way of thinking about things. It's a different type of problem than a lot of things you've probably dealt with, and they're really fun to work with just because of the graphical nature of the output. The downside is that if you have a bug in a shader, it's really hard to debug because there's no like debugging tools for shaders really, in the sense like you can't print out a number. If you need to debug a shader, you have to do the equivalent, which is set a color to a specific thing so that you can see what your numbers are. So like if you don't know what a number is in your shader, you put it into the pixel you're outputting, and then you will debug based on the colors you see and stuff like that. So it's a bit tricky. Anyway, that's pretty much everything I wanted to show you for this tutorial. I know it was really long, but this is a very complicated topic. There's a lot more you can do with OpenGL and ModernGL. And if you look at some of the examples in, well, you can look at Hue Flowing, which I mentioned. That's the only like free thing where I've released the source already I can think of right now. You can see how I use all the uniforms and everything. There's the different types of uniforms. You can learn about GLSL a little bit from there as well. I'll link that in the description. I'll also leave a link to the ModernGL documentation. There's also a ModernGL Discord server where you can ask some questions. There's also my Discord server where you can ask questions. So that's pretty much everything. I hope you learned a lot about OpenGL here and ModernGL. I guess I'll see you guys in the next video.